Welcome to Lecture 11 for Chemistry 312. This is the lecture on chemical speciation. This is the first lecture that covers the chemistry in Chemistry 312. In this lecture, we're going to explore the chemical form of elements and discuss how to understand what conditions are responsible for forming certain chemical forms. This is important for radionuclides, in which we want to manipulate the radioactive isotope. By doing so, we need to change its chemical form so that the radioactive nucleus travels where we want it to go based upon the prevalent chemistry. Speciation is important in understanding the behavior of radioisotopes in separation systems, in nuclear fuel, in the environment, in waste forms, radiopharmaceuticals. It can be applied in numerous areas for manipulation and utilization of nuclear technology. In this lecture, we're going to discuss the use of constants to model chemical form. We're going to review thermodynamic and kinetic data, and we're going to talk about how the property of a radioelement is based upon the speciation, so that the chemical species in the system, the chemical form, is the dominant route in which we can understand or control the radioactive isotope. As an example of that, here's a figure that shows an overview of actinide behavior in the environment. We see that there's a number of different neptunium species. We start off with a neptunium compound in the middle, so it's neptunial. We'll discuss the chemistry of neptunial in later lectures. But this neptunium is sitting in water. It's surrounded by 5 waters, and it's, in this phase, it's mobile, it's soluble. And a few things can happen to it. We can change the oxidation state. So we can make the neptunium go from 5 to the 4. The chemical form will change because the behavior of the 5 of pentavalent neptunium is different than tetravalent neptunium. This will have an impact on the behavior of this neptunium. This neptunium can be in a solution phase and can complex with something like carbonate. Now, instead of having neptunium surrounded by water, we now have neptunial carbonate. This neptunial carbonate will behave differently than an aqueous species. We can also talk about precipitation. So, for instance, this carbonate species, if this aqueous species reacts with a carbonate, makes a carbonate species, this carbonate species can also precipitate. Obviously, if it precipitates, it comes out of solution, different behavior. This chemical form, this aqueous species, can sorb to a surface. So this sorption property, again, retards or retains this metal ion on a surface. So in the environment, this could be sorbing to a clay phase, it could be sorbing to an organic phase. And there's also another reaction where a biomolecule or a biological system, for instance, microbes, can interact and change the chemical form and change the speciation by absorbing them and making these compounds now a biological molecule where it's incorporated or sorbed to a microbe species. All these different species will have different transport properties. So imagine if I have neptunium in the environment, if there's some neptunium in an aquifer, how does it behave? All these chemical reactions come into play. And we can determine the speciation, the different chemical forms, based upon constants. So in this lecture, we're going to review equilibrium constants. We're going to talk about activity, chemical activity, as opposed to radioactivity. And then we're going to give an example of the use of constants to determine and calculate the speciation of metal ions. For any reaction at equilibrium, we can evaluate a constant that should describe the concentrations. So here we have a generalized reaction, A, B going to C plus D. At equilibrium, the ratios of the products and reactants is defined as a constant. And by convention, these constants are expressed as products over reactants. And the equation, we get some constant here, is equal to the products with raised to the exponent their stoichiometry, divided by the reactants. Now these constants, although they're constants, they can change with temperature, ionic strength, and if you measure constants or if you see them in the literature, you should try to understand what are the explicit conditions that these constants were measured under. Often you will get ionic strength, the type of ion that was used to adjust ionic strength, and even temperature. But strictly speaking, these are concentrations. One should really use activities, which are listed in this equation here. We have activity coefficients. At low concentrations, activities are assumed to be 1. And what one can actually do to try to evaluate some of these activity coefficients is to examine constants over a range of ionic strengths and fit the activities. Now there's a number of different equations that are used to evaluate activities. One of the earliest is the Bi-Huckel equation listed here. Rather straightforward equation. Here's your activity coefficient, where we have some constants, where some of the conditions involved in here are the charge of the species, the molal ionic strength, so not molar but molal, and the hydrated ionic radius in angstroms. You can develop a term for the Bi-Huckel reaction, which is listed here in this equation, where we just get this term as a function of the square root of the molal ionic strength. The Bi-Huckel terms are useful for extending activities to higher ionic strength. The Bi-Huckel equation is really reasonably good for low ionic strengths. And there are a few activity terms and equations that have been developed to examine higher ionic strength. We'll talk about one, the specific ion interaction theory, where you expand the Bi-Huckel term. So we have this Bi-Huckel term, this D, which is the same as here. It has a short range and a long range term. So there's a long range Bi-Huckel term and a short range specific ion interaction term. And when we say specific ion that will interact with the metal ion that you're interested in evaluating, chlorides, nitrates, etc., have different specific ion interaction terms. One can wrap up all these terms together and develop an equation which says the log of the complexation constant at a measured ionic strength is equal to a 0 ionic strength plus this function of the Bi-Huckel term minus the specific ion interaction terms times the molal ionic strength. There's a final equation, the Pitzer equation, which has 3 binary terms and 2 ternary terms that describe the interactions, and information on Pitzer can be found on the internet. Overall, by evaluating the activity as a function of molal ionic strength, there's a few conditions that one can evaluate. This figure here shows activity coefficients for different sodium salts as a function of ionic strength. For different calcium chlorides, lithium bromide, lithium chlorides here. And then activity coefficients in this figure here showing ionic strength variations from low ionic strength to seawater levels with different ions. And some of the trends that are obvious here is that the monovalent proton, sodium, potassium, have activity coefficients that are higher than the divalents, and then those divalents are again higher than the trivalents. So there are some trends that can be identified. Here's some data showing the complexation constant measured for humic acid and curium as a function of the square root of the molal ionic strength. If you remember the specific ion interaction term, there's 2 terms that are functions of either the molal ionic strength or the square root of the molal ionic strength. And by plotting the equation where we get the complexation constant measured at a given ionic strength is equal to the complexation constant at 0 ionic strength plus the long range and specific ion interaction terms. We can plot that. This was done for this data, and we can develop this line will give us the equations that will determine the specific ion interaction terms. Okay, there's a number of ways that constants can be presented. A very simple one is an equilibrium constant, where you get some bond breaking and bond making. So imagine I've got just some acid of some sort where you get 2 protons formed and some sort of polymerization occurring. I can have a very simple reaction that describes this. I can also talk about stability constants or formation constants. And imagine we have plutonium with carbonate going to plutonium carbonate. Again, the complexation constant for this would be the concentration of the plutonium carbonate divided by the concentration of plutonium-4 times the concentration of carbonate. This same reaction can be written as a conditional constant below here, where we have the plutonium-4 plus the protonated carbonic acid going to the plutonium carbonate plus protons. Now, if we have something like protons in here, we can imagine within this equation that this constant is going to vary with pH. Overall, if you use constants from the literature, you should evaluate what equations those constants relate to. Okay, so once we have a reaction, we can use this information to develop a complexation constant and either measure the complexation constant, or if the complexation constant is known, calculate equilibrium conditions. So let's go back to a very simple system where we have this reaction 2HX going to 2 protons plus a dimer of X minus 2. This constant here, let's assume it's 4 times 10 to the minus 15. You can use this to answer equation. Initially, if you have 1 mole of HX, what are the concentrations of all species at equilibrium? So if we think about this, we can write a reaction here. We have the complexation constant here. Now we can try to make some terms and substitute so that we can solve for the different species at equilibrium. So to write this, what one would do is evaluate which species would have the lowest concentration at equilibrium. And there's a hint here, since the complexation constant is a very low, small number, I expect that this reaction does not proceed strongly in the forward direction. At equilibrium, it's going to be primarily primarily reactant, not so much with the product. So if we say that this dimer is equal to X, the proton concentration is twice the dimer concentration, and then the concentration of the starting compound is just equal to 1 mole minus 2 times X, because it takes twice the X, so I need to multiply the value of X. Well, since K is small, X must be small. And 1 minus 2x we're going to approximate with 1. So this is a way of solving this equation with a little bit of some terms that makes it easier on us, so that we can rewrite the equation where K is equal to, this is our proton concentration. Excuse me, this is our proton concentration. This is our dimer concentration, and this is the concentration of the reactant. We're going to say the concentration of the reactant is fundamentally 1. This becomes K is equal to 4x cubed. If K is 4 times 10 to the minus 15, 1 times 10 to the minus 15 is equal to x cubed. X is equal to 1 times 10 to the minus 5. So this dimer is equal to 1 times 10 to the minus 5. And so we solve for the X. And we know that twice this amount is equal to the proton concentration. And the concentration of hx, well, that's just equal to 1 because we set that as part of the approximation. All right, so that's a fairly straightforward and simple case. Now let's try to evaluate a more realistic case. In this more realistic case, the metal ion of interest may be in a complicated environment. There may be many different species to consider simultaneously. So as an example, consider the speciation of uranium in an aquifer. And even in this case, we're going to make it pretty simple on ourselves. And what we're going to do is limit the species that we're interested in, that we're going to calculate for. The uranium species are either going to be the free uranium, some form of uranium hydroxide, some form of uranium carbonate, and then some form of uranium bound with natural organic matter. We'll call those uranium humates. Now we need to get the complexation constants for the species that we're interested in. For example, if I'm interested in the carbonate speciation, I need to get the complexation constant that describes this reaction. So that would be the concentration of the uranyl carbonate divided by the concentration of the free uranium times the carbonate. So fundamentally, I need to know or find the total uranium, the total carbonate, the pH, since that's going to be an important component, and the total humic acid concentration. Lucky for us, there's extensive databases that are available that can provide complexation constants for a number of species. And here are listed some of the relevant complexation constants for the uranium species that we've discussed. So here are the hydroxides, and here are the carbonates, here are the humic acids. A lot of this data can be available for uranium from the chemical thermodynamics of uranium. The link is listed here. The link is also on the web page. There's other ways that we can make this easier on ourselves. If we know the total amount of uranium is low, we can exclude binary or ternary species. So if we have a low amount of uranium, we can just exclude these species from our calculations. We don't have to worry about them. Okay, so we can find the complexation constants. Now what we need to do is write our equations. And what we want to do, we want to describe the total uranium concentration in solution, which we'll call this U total, as the sum of all the uranium solution species. So for example, the U total is going to be equal to the amount of free uranium plus the amount of uranium carbonates, and we had a few uranium carbonates, and the uranium hydroxides. Make sure that if you have something like the uranium hydroxides, if you have dimers or trimers, you need to include that, the fact that you have 2 or 3 uranium in those molecules, and uranium humate. Since carbonate is a function of the speciation, we also need to know something about the carbonate concentration. We can actually get the carbonate concentration as a function of pH. If we utilize Henry's constant for CO2, in other words, if I know how much CO2 is in the gas phase, Henry's constant will tell me how much goes into an aqueous phase. That'll form carbonic acid. And if I know my protonation constants for carbonic acid, I can actually write an equation where the log of the carbonate concentration is equal to the log of the constants plus the log of the CO2 partial pressure minus 2 times the log of the proton concentration. And knowing that pH is just minus the log of the proton concentration, I can substitute pH in this equation for log proton concentration. So I can derive an equation that tells me the log of the carbonate concentration as a function of constants, and the partial pressure, and the pH. I also need to know something about the hydroxide concentration. Well, I just get that straight from the pH, where POH plus pH is equal to 14. That I can use to derive the hydroxide concentration at any given pH that I care to measure. And then the total amount of humic acid is equal to the different uranium species plus the amount of free humic acid. So now I have all my terms to describe the range of species that I'm going to be interested in evaluating. solve for the speciation, what one needs to do is write all the species in terms of free metal, free ligands, and the constants. As an example, we have a generalized complexation constant here for a uranium with ligand A and ligand B that's formed from uranyl, so free uranium, free ligand A, and free ligand B. The complexation constant is written as this XAB because this tells me how many uraniums, how many ligand A and ligand B there are involved in the complex. If I have this generalized complexation constant, I can write the concentration of the product as a function of the complexation constant and the species involved in the reaction. An easy way to evaluate these terms is to write the free ligand and free metal concentrations as px values. Px, like pH. Px is just equal to minus the log of the free concentration. So for instance, P uranyl, UO2 2 plus, is just equal to minus the log of the UO2 2 plus concentration. I can rearrange this equation so that I can put these px values in along with the complexation constant to calculate the species of interest. I need to include the negative of the log of the complexation constant since I'm talking about px terms, so I just treat this as a minus the log term. And what this becomes is that the concentration of the species is just equal to 10 to the negative x p metal, so p uranium, plus a pa plus b pb minus log of the complexation constant. And these factors that I have out in front is just the stoichiometry. The x is how many uraniums are involved in the final complex. This small a is how many ligand A, and the small b is how many ligand B. As an example, for this diuranium dihydroxide species, this species here, the constant to calculate it, it's equal to 10 to the minus 2 times the PuO2 plus twice the POH minus 22. That comes from the complexation constant being log, the log of the complexation constant is equal to 22. So I can set up all these equations and solve. Now that we've discussed how to set up these equations, the next step is to actually solve for them. We're going to give a few different examples, two primarily, one using an Excel spreadsheet to set up the equations, and a second one using a program called CHES. CHES is a speciation program, and it's one of many available programs, both commercial and freely available, that one can use for speciation calculations. Here's an example of an Excel spreadsheet that could be used to determine the speciation of uranium as a function of CO2, partial pressure, and pH. The data, the thermodynamic data that we're going to use are listed here. Here are the pKa's for the carbonic acid, combined with Henry's constant, the pKw for water, and then here are the thermodynamic data for the different uranium species. Here's the way they're designated, and here are the log values, and these are provided for all the species listed here. So uranium carbonate, uranium hydroxides, and then we have some data for humic acid. We're going to evaluate the speciation from pH 1 all the way to pH 10. Our CO2 partial pressure is listed here. Our total amount of uranium is 2 times 10 to the minus 7. We can easily change this by just varying this value. Our total humic acid is 3 times 10 to the minus 4. That can change easily. And then we can use these terms to derive these calculations. Now that we have the thermodynamic data in place, all we need to do is calculate the species. Since we have the thermodynamic data, we need to determine the PM values, so the P metal, UO2, and the PHA. What we do, we just start off with a value that's realistic. If this is our total amount of ligand and total amount of humic acid, total amount of uranium, the PM values should reflect that. And so for humic acid, the concentration is 3 times 10 to the minus 4. Saying a free metal concentration of 10 to the minus 4, that's less than the total, so that's realistic. And the same thing with uranium. If it's 2 times 10 to the minus 7, we say the free concentration is 10 to the minus 7, that's realistic. Now that we have these numbers, we can calculate all the species for each pH. We don't know how accurate these species, the actual species calculations are. We can assume that they're actually not accurate because we've made a guess. However, we can calculate the percentage of humic acid and the percentage of free uranium that's available for each of our calculations. So all this is saying, out of all the data that we've calculated, the percentage of free uranium is listed here. It's just the concentration of the free uranium, so it's 10 to the minus 7, divided by all the uranium species. And for instance, this one, it's 2 times that value because we have 2 uraniums. So that gives us a percentage. If we have a percentage, and I know the total value, which is 2 times 10 to the minus 7, I can recalculate my PM value, which is what we have here. It's just the percentage here times the total, the opposite log of that value. That's it. We do the same thing for the humic acid. Now all I need to do is take these values and copy them and paste them in the original value. I copy, I go back here and paste, and the one trick is you want to do a paste special, and I want to paste the values. I do that, and you see these values have changed. I've done another calculation. They've calculated another set of values. Now, as opposed to doing this manually with Excel, we can record a macro. So I'm just going to make this Control A. So what I'll do is, this macro is running. I copy the calculated px values. I move these back to my initial px values. I say paste special, and I paste the values. And then let's go back here. I stop recording my macro, and remember it was Control A, so every time I press Control A, I recalculate. I can write this macro to do that 100 times. I can check the values, and I wind up with the percentage that is, I can get an evaluation of the total amounts. I can get the absolute values. Here are all the concentrations of the species in mole per liter. I can calculate the percentage of each species, and this all varies as a function of pH. So now I have this tool that allows me to determine the speciation under any of the conditions that I'm interested in evaluating. I can change pH, I can change total uranium, total ligand, and even the CO2 partial pressure. One way to improve upon the Excel speciation spreadsheet would be to generalize the way the thermodynamic data is presented. In the previous example, we have to explicitly write the complexation constant and provide within the cell the correct PM or PX values one would want to use. A generalized route would involve writing a table that has the constant, the number of metals, the number of ligands, the number of protons, the number of hydroxides. That way you can write a generalized equation that includes all the relevant PX values, but the factor, if it's 0, takes that out of the equation. I'm not going to go and do a calculation using this cell, but just wanted to show you that there's other ways, other routes that one can use to determine speciation through Excel spreadsheets. And I also understand that this was a relatively fast, and if it was your first time, it might not be particularly clear on how all the speciation is performed. But what one can do for that is review the equations and practice with the spreadsheets. And both those spreadsheets are available on the web page. One of the main outputs for the calculations we've just performed is the evaluation of speciation of uranium as a function of conditions. And here's the data for 0% CO2 partial pressure, 1% and 10% CO2 partial pressure for uranium speciation as a function of pH. And this data is taken from those Excel spreadsheets. And what we see is that as the CO2 partial pressure goes up, the carbonate becomes more important, it becomes more dominant at earlier pHs, and that the overall concentration of other species are impacted. For instance, this mixed uranium hydroxy humic acid species, that seems to be impacted by the level of carbonate because it's competing for carbonate speciation around the same pH. One can also use the data to evaluate the amount of organic matter, colloids, that would be present. So we've used the summation of all the uranium colloids to look at the complexation and formation of uranium colloid as a function of CO2 partial pressure. And what we see here is that there's a noticed impact of CO2 partial pressure. We go from 100% to 0%. We see that the amount of colloid at higher pHs increases if there's no carbonate present. Another simpler way to perform speciation calculations is with a commercial available model that has a database embedded in it. As an example, we'll use the CHES model, the JCHES, and this is the link on the model itself, and the manual for the model is available on the web page for this lecture. And we'll quickly show how to do a very simple speciation of uranium from pH 2 to pH 10. So we'll start here. We'll say we'll add some of the values and variables that we're interested in. So we'll add a pH value. I said we'll go from pH 2. We'll start at pH 2. We'll say apply. We'll add a basis species, and let's put in UO2, 2 plus, and we'll say that it's 1 millimole per liter. We'll apply, dismiss, go to reactions, we'll add a variable. We want to go from pH 2 to pH, let's say 12, dismiss, and we go from pH from 2 to 12, that's our variable. Now for the output, we'll say let's output pH, so we can plot it against pH. Groups, if you use all, you'll get error. There's an error in the program. So if I go to groups, I'll say let's look at the aqueous. It's in millimoles, apply. We see that it's listed here. And then minerals, solids, anything that precipitates out, apply. Dismiss. And now we're ready to run the speciation calculation. Go over here to CHES, say run CHES, and here's our result. We get a graph that shows concentration versus pH. And we can't tell much from this, but if we look at this graph carefully, there's some data here that I'm not interested in plotting, like the proton concentration versus pH. That's trivial. So let's go back to the JPlot tab here. So this is what we're plotting, pH versus everything here. Let's eliminate those species we're not interested in. I'm not interested in the proton, so I'll remove it. And I'm not interested in hydroxide, and I'll remove it. Everything else, I'm interested in Shopite. That's UO2OH, 2, solid. And the line's yellow. I don't want it to be yellow, so we'll click on the line, and I'll make it purple. And to make it a little bit more noticeable, we'll change it up. And I go back and I plot it, and there we see that the concentration varies as we go from pH 2 to pH 4. The free uranium decreases. The Shopite, this precipitate, is dominant from pH 5 all the way to around pH 10. We get above pH 10, we start forming this species here with the UO2 hydroxide. Okay. So we can use this same database. We can go back to the main solution, and let's say I'm going to change the total uranium concentration. It's in millimole. Let's go to micromole. And I'll apply that, dismiss. Everything else is the same. Let's have chess run it again. Again, it gives me the output that includes the proton. I'm not interested in the proton. I'll eliminate the proton, eliminate the hydroxide, and I click here. Oh, and I get my speciation curve. Now what we see at the lower concentration, we don't have the precipitate. The uranium free concentration decreases. This uranium hydroxide species increases. And finally we get this uranium hydroxide species. Okay, chess can be used for a number of metal ions. If we were to look here, we could add plutonium, americium, not technetium. If we wanted technetium, we might have to go to some of the aqueous species. And here's the technetium species. This was just a very brief introduction. More information can be found by working with the program and reading the manual. Chess can also do solid reactions, including development of EH-pH diagrams. Thermodynamic data, particularly the complexation constants, as we've already demonstrated, are useful in determining speciation. But by measurements of the complexation constants, we can actually evaluate other thermodynamic data. As we discussed earlier, there's relationships between the Gibbs free energy, enthalpy, and entropy, but also the Gibbs free energy and the complexation constant. So here's an example of some experimental data of the complexation of neptunium with humic acid. We've measured the complexation constant, and what we're plotting is the R natural log of the complexation constant against the inverse of the temperature. If I took these two equations and rearranged them, I can get R log K is equal to minus delta H divided by T plus delta S. This allows me to solve the slope. The intercept will give me delta H and delta S values. If I have the delta H and delta S values, I can determine the Gibbs free energy at any given temperature, and that data is actually presented here. So through the complexation constants, one can evaluate thermodynamic data. Conversely, if one has the thermodynamic data, enthalpy, entropy, or Gibbs free energy, one can determine complexation constants. Solubility products are also some thermodynamic data that can be useful in determining speciation. Here's the example of the dissolution of silver chloride, where the silver chloride solid goes to the silver and chloride ions. If we were to write this as a K, we'd use this equation. However, the silver chloride is solid. Its concentration is fundamentally constant, so we can actually drop out of the equation. We use this this concept for evaluating KSPs, are often written as K with lowercase sp, and that's equal to the concentration of the ions that are produced in the dissolution of the solid. One can evaluate complexation constants, for instance, by taking some of the solid and dissolving it. So imagine that we have some silver chloride, we put it into some water, we measure at equilibrium that the silver ion concentration is 1 times 10 to the minus 5. Imagine we did this with a ICP-AES. The question is, what's the KSP? Well, if I just start off with silver chloride, I know that I make silver and chloride. For every mole of silver, I'll make 1 mole of chloride. So those concentrations are equal. So the KSP is equal to this 1 times 10 to the minus 5 times 1 times 10 to the minus 5, or equal to 1 times 10 to the minus 10. If we had the KSP for a salt, for instance, magnesium hydroxide, we could calculate the solution phase concentration of the metal ion at any given pH. So here's an example. What's the concentration of magnesium at pH 10? We use the KSP, which is 1.2 times 10 to the minus 11, is equal to magnesium times the hydroxide squared. We rearrange this equation, knowing that the hydroxide is equal to, if I give you the pH, 14 minus the pH is equal to the pOH, so 10 to the minus 4. I rearrange this equation where the magnesium is equal to the KSP divided by the hydroxide squared, and I get a value of about 1 millimolar. We can use this with uranium. Here's a literature value for the KSP of the for uranium dioxide. The value is 10 to the minus 52. If I use this value, what's the expected uranium-4 plus concentration at pH 6? And then generalize the equation so I can measure, so I can calculate the uranium-4 concentration at any pH. Now, in an actual solution, if the uranium-4 then oxidizes to the 6, your total amount of uranium in solution would be much greater than what you calculate from the KSP. But let's use this as an example. The solubility reaction listed here, where I have the uranium dioxide, water gets added to it, I make this species, the uranium OH4. That then dissolves into the tetravalent uranium species and 4 hydroxides. The KSP is just the products of the uranium and the hydroxide is raised to the 4th. So the amount of uranium-4 that I can calculate is just the KSP divided by the hydroxide concentration of the 4th. If I remember that the pOH plus pH is equal to 14, I can say that at pH 6, pOH is 8, so the hydroxide concentration is 10 to the minus 8. 10 to the minus 8 times 4 is 32. So the concentration of uranium-4 is 10 to the minus 52 divided by 10 to the minus 32. That's equal to 10 to the minus 20. And I can generalize this equation where I've said, well, I'm just going to plug this into here where I say that the uranium-4 concentration is just equal to the KSP divided by 10 minus 14 minus the pH times 4. If I take the log of both sides, it's just 52 plus pH, 14 minus pH times 4. So that's a very generalized equation that I can use to determine the amount of uranium-4 that will be formed from the dissolution of uranium dioxide. There are some limits of KSP. Colloids. KSP does not include colloids. In fact, thermodynamic data do not explain colloids well at all. So if you do have colloid formation in your solution, that will actually not show up in thermodynamic calculations. So your calculations versus your experimental data may vary. And often you can have formation of other species that aren't considered in the KSP. For instance, with silver chloride, if I have excess chloride, I can form an anionic soluble species. KSP values are really best for slightly soluble salts. What was presented in this lecture includes reaction and complexation constants and the role of activity, chemical activity, in those constants. As was shown here, we can have a reaction where we get some reactants going to some products. The complexation constant or some equilibrium constant is shown here where we have the products divided by the reactants. Here we have the chemical activity included. So these are the equations that we use to determine speciation. So if we have this value known at equilibrium, we can determine the relative concentration of each species. We also discussed how to perform these speciation calculations, provided an example with a simple system using an Excel spreadsheet, and a more complex system using a program. In this case, we used the CHEM program for chemical speciation. Another thing we did, we discussed the relationships between Gibbs free energy and complexation constants, exploiting this equation here, where we have the Gibbs, and then we also can use the equation where the Gibbs free energy is equal to delta H minus T delta S. We can relate these two terms, and we can show how we can get the delta H and delta S from a reaction based upon its complexation constant. So if you measure the complexation constant as a function of temperature, the thermodynamic terms for a system can be derived, including delta G, D. Since we know delta H and delta S, we can get all the terms. Some specific questions you should be able to address based upon the lecture are shown here. For instance, provide complexation constant for the formation of plutonium monocarbonate. Well, the reaction is shown here, where plutonium interacts with carbonate, forming the plutonium monocarbonate species, and the complexation constant would be the concentration of the plutonium monocarbonate species divided by the concentration of plutonium free times the concentration of the carbonate free. This equation is not shown with ionic strength corrections or activity coefficients. In fact, you would need to discuss what are some conditions that can influence complexation, for instance, temperature and ionic strength, and often these conditions should be explicitly provided. So for instance, you may perform the study here of plutonium carbonate. It may be performed in 1 molar ionic strength. So you would say that the complexation constant that you've measured is at 1 molar ionic strength. Then you can even report the temperature as 25 degrees or room temperature. And what are some equations used for evaluating activity coefficients? Well, we've discussed the Debye-Huckel, which is a very fundamental equation you've probably seen in previous courses. The specific ion interaction theory, which engages more terms and tries to bring in more of the chemistry that is occurring with the anions and cations that are acting as spectators or changing the ionic strength. And finally, we also discussed Pitzer equations, which are even more complex than the specific ion interaction theory. And both the specific ion interaction theory and Pitzer equations are really trying to evaluate conditions where you have high ionic strength. Another question that you should be able to answer based upon the lecture is something to the effect of, well, determine the speciation for 100 millimole per liter americium-3 and determine the speciation from pH 1 to pH 12. What one would do, you could use CHEM, input the americium concentration in the pH range. This would have the way of accessing all the constants in the CHEM database, and you can develop a figure that would look like this, where you would see that the concentration of americium-3 is dominant at the lower pH. As you increase pH, it starts to tail off. You get the monohydroxide forming a little bit of this dihydroxide, and then around pH 7 you start to get the americium trihydroxide form. When you've completed this lecture, please comment on the blog and respond to PDF Quiz 11.